Hey everyone, I hope the exam went well for all of you guys. There's not too much new material on this action center, so it should be pretty short. This first one that I've picked here is just because you're going to see this a lot moving forward, and especially getting into like metabolic reactions, you'll see this a lot. So it's a good thing to get in the hang of doing. It's basically a Hess's law question, so you take your two half reactions and you're going to add them together so that you can get this as your final reaction. So in the final reaction, you've got your elemental copper on the left hand side and your elemental iron on the, or I'm sorry, that's the right hand side, and your elemental iron on the left hand side. So we're going to have to flip the second equation. So it'll just be Cu2 plus the 2 electrons gives you Cu, and then we reverse the second one, so iron 2 plus 2 electrons. And so we've got our reduction potential of plus 0.3 volts here, and we flip this one, so this one will be plus 0.4 volts. And when we cancel out all our terms, we'll get the desired equation, which is the iron plus copper 2 plus, yielding iron 2 plus elemental copper. And then we add down for the reduction potentials, and we'll get plus 0.7 volts. And that is our reduction potential. So for the cooperative protein question, we're given the equation Y, so Y is fractional saturation, is going to be equal to the partial pressure of O2 in whatever place we're dealing with to the nth. Nth is a measure of cooperativity over the P50 to the N. P50 is the half saturation point, the partial pressure at which the protein is half saturated with ligand, plus the partial pressure of the O2 again. And so the question's asking us to find like the difference in fractional saturation of oxygen in the lungs versus in the tissues. So what we're going to do is, so to calculate Y in the lungs, he's given us that PO2, the partial pressure of oxygen is 100, and the cooperativity of our protein is 3.1, over P50 is 24 to the 3.1 plus 100 to the 3.1. So that's going to give us 0.9882. And then so in the capillaries, we'll do the same thing, but this time we'll change the pressure. So because it's 25 torr in the capillaries, but the N term will stay the same because the cooperativity of that protein will stay the same. Over 24 to the 3.1 plus 25 to the 3.1. And that's going to give us 0.5316. And so to find the difference between these two fractional saturations, it'll just be these two values subtracted and then multiplied by 100 to give you the percent. So we'll get 46%. And that's the difference between, the saturation in the lungs minus the tissues, which makes sense if you think about it, because, the purpose of the lungs is to supply the blood with hemoglobin, and that's because there's such a great partial pressure of oxygen in the lungs compared to in the tissues, where you would actually need the oxygen to go to the tissues to be used. And so the last one I chose here was this one about the protein calcineurin. And so he's asking to find the dissociation, the K off. And so the way that I like to think about these is that, so I've got some protein and I have, its ligand. So whatever protein plus the ligand is going to be in this reversible reaction with the protein ligand complex. And so our forward arrow is the rate K on, our backwards arrow is the rate K off. And so we're given that K on is 8.9 times 10 to the third per molar per second. And we also have KD, the overall dissociation of 10 nanomolar. So the formula to calculate K off then, so KD, the total dissociation constant, is going to be equal to K off over K on. And so if we want to find K off, that's going to be equal to KD multiplied by K on. That's going to give us the value for K off. So KD is 10 nanomolar, and we're going to want to convert that to normal molar because that's what our K on units are, so we want the units to work out. So 10 times 10 to the minus 9 times the value of K on, which is 8.9 times 10 to the third. That's going to give us 8.9 times 10 to the minus 5. And then we'll need to find units here as well. So the units for our KD it was just, it would have been molar when we calculated it, or after we converted it, sorry. And then this one would be 1 over molar per, or times seconds. So these would cancel out and we're left with inverse seconds. And that's our answer.